Okay, let's talk about Section 2, high voltage equipment. Okay, in this section we're going to talk about power plants, substations, transmission, and distribution. Okay, so the learning outcomes for this section is to describe various electric generation power plants commonly used in bulk power systems. We're going to discuss all types of major equipment used in substations. We're going to describe the components and their purpose regarding overhead and underground transmission lines. Okay, so we have these learning outcomes. We're going to learn about generation, substation equipment, and power lines. We're also going to discuss the types of distribution facilities and their components and operations. Okay, we'll get into overhead, underground, what have you, and we're going to apply terminology and concepts already learned to electric power system simulator. Okay, that's what this type of information is going to be applied to the simulator. All right, so Module 5, which is power plants. It's a picture of a power plant right off of Lake Shasta. And you can see the water and coming through the pipes here on the side where the water's flowing through to the generators down here and the substation and power lines distributing the power. Okay? So the learning objectives for this module are discuss the different types of power plants, steam, nuclear, wind, solar, etc. Describe the equipment and systems used to heat, cool, recycle water in a process of converting different energy sources into electrical energy, like the boilers and turbines, etc. Identify the symbols used by the power system simulator and describe how to use the power system simulator. Okay? So, starting out with steam turbine power plants. Here's a picture of a steam turbine at a power plant, and what we have is the generators right here. This is the generator, and this is the steam turbine. This is what's providing the prime mover, turning the generator. This little compartment over here is the exciter. That's where you find the slip rings, and that's where you're putting voltage onto the rotor of this generator. Okay, so this is a steam turbine power plant. Here's inside what the turbine blades look like, okay, of a steam turbine. Okay, and then now a little bit on a coal-fired plant that uses a steam turbine. Okay, so here we have a conveyor belt that has coal, like chunks of coal coming up here, and then it goes into the pulverizer where the coal is put in more of a powdered form and blown into the furnace where it's then ignited and heating up steam so we can create steam for the steam turbine. Okay? And it basically looks like this. We have, in this case, coal coming into the furnace, which is part of the boiler system here, and we're taking water from a different system of water and we're superheating it. It's cool here, and we're superheating it to become dry steam, approximately 1,000 degrees Fahrenheit, and a high pressure, 2,000 psi. Going across the blades of the turbine, spinning the turbine, which is connected to the generator, okay? And the steam, after being used on the blades, actually, the high pressure steam goes into a large volume, so the pressure is going to drop because it goes into a larger volume area. Pressure drops. We're taking the high temperature steam and spinning the blades at the temperature of the steam is going to drop. The pressure drops, the temperature drops. We come through here, and now we have a lower temperature, lower pressure steam that we condense by letting that fall on cold water pipes that are circulated from either a river or underground water or ponds or the ocean. And that steam hits those cold pipes, and when it hits the cold pipes, it condenses and becomes drips of water again. The water is collected on the bottom and then pumped back to the boiler where it's superheated again. So the steam is going through that superheated cycle and condensed down to water and back up again, so it goes through a full temperature swing. Meanwhile, the generator is putting output to the to the transformer and then into the system. This is a basic steam turbine system using coal as the energy source. Okay, here we have a combined cycle. In this case, we have like a jet engine that's being run by either natural gas or some type of fuel to run the generator, and actually to the steam, the exhaust from the jet engine, the thrust out of the back of the jet engine is turning a turbine, which is producing electricity with a generator, and that heated exhaust then goes through what's a heat exchanger, where there's another cycle of water that's being superheated or heated to whatever temperature it can get to be able to drive a steam turbine. So you actually have two generators. One is from the jet engine or a combustion engine that is generating that generator, and then the heat is through a steam turbine, that generator. So the two outputs, which is called the combined cycle system, is what's going on in this type of a power plant. There's a lot of these around. It's got a high efficiency, but you have a cost of fuel. Okay, so that's a combined cycle system here. Here we have a nuclear plant, and here we have containment walls that are housing the nuclear reactor, and a air tower or a cooling tower where instead of using water for the ocean water or pond, we're actually using a slightly different system. We're actually cooling the water used to condense via airflow, okay, and air cooling. It's a little different. Okay, so what we have is a containment structure that has a reactor that is producing high temperature water from the heat, which a separate water system, it goes out to the turbine. So we're using the reactor to produce heat, to heat exchange into a secondary water system, which is then going through the turbine blades, back being condensed. This time it's condensed through cooling towers where air goes under and up. Okay, and we're bringing the water, we're bringing heated water, bringing it back cooler so we can condense the water flowing through the reactor here back into the containment structure where it's superheated again. Now we have control rods here, which if the rods were dropped down would turn off the reactor, and lifted up would increase the heat reaction in the reactor. And this is another form of producing steam turbines. So at the nuclear plant we have steam turbines just like you do have at a coal plant or even a geothermal plant. I mean, there's different characteristics, of course, but the process is still a steam turbine generator. Okay, in a hydro plant we're going to talk a little bit about how the water comes down penstocks here into the generators which produce electricity that direction. A couple different ways of doing it. This is the picture over at Hoover Dam by by Las Vegas. Hoover, Boulder Dam, kind of dual name. And these turbines are being turned by the water flowing underneath. Here is a penstock where you have water coming down through a kind of a squirrel cage type of turbine, water going out, generator sitting on top. Different ways of producing water. But water moves a lot slower than steam. That's why you will see multiple poles on the rotors on a hydro plant. So because you don't need to spin the rotor as fast, and that's it's very common to do that on hydro plants. All right, when we talk about geothermal plants, a little different. Take some of the steam out of the earth. It's kind of it's not the cleanest. It's got sediments. It's got impurities. It's not real clean steam. So the steam is normally brought through a heat exchanger, so that another water system gets the heat from the steam, and it gets put back into the earth. But then this is what's heated up here, and then that goes through a steam turbine. And then you can actually use some of that steam to operate some of the plant, some loads. For example, paper mills need steam to manufacture paper, or fish farms to keep the water temperature at a certain temperature for growing fish. So you might use that steam for other purposes before it actually gets recycled or put back into the earth. So the problem with the geothermal is you have to be at the locations where there's geothermal. Now there are locations, but it's not everywhere, so you're kind of limited to, number one, the temperature of the steam that's coming out, number two, the location. So they're around, but it's nice to have heat sources that are free, but you have issues that go along with that. Now when it comes to wind power plants, you have the blades that you see, everybody has seen, but there's a couple characteristics about it that I want to kind of go over with you. This particular picture actually has windbreaks on the outside. Actually, the end of the tips, you can turn them so they can become paddles to slow it down, because if you have high wind gusts, those things can spin so fast they can come loose or break down or fail. So there's a little bit of wind breakage there. Also in the nacelle here, where you house the equipment, that turns in the direction of the wind. You can optimize its performance. The blades can pitch in and out to control how much cut. What's interesting about wind, if you get into wind, the wind generation, the formula for how much power you get out of the wind has a term at the wind speed cubed. In other words, the power is associated with the cube of the wind speed. So when you get a gust, you really get a sudden surge of power. So you have different control mechanisms to kind of adjust that. Most of the machines today are spinning fairly slow because they have gearboxes and they have multiple magnets on the rotors. And a lot of the smaller wind turbines don't have electromagnets, they use permanent magnets. So, and they could be at any frequency. So then if you have wind, high speed, different frequencies being produced because of the spinning isn't consistent, you convert the frequency to DC, then you can invert back to a controlled 60 cycle AC to go back into the system. So there's different ways of working with wind generation, but that's becoming pretty popular, especially in our east and west grids. Starting to get quite a few wind farms out there. And there's some interesting dynamics about wind, and some of the other courses that we have will talk about variable generation dynamics, and sometimes on low voltage ride-throughs, and a lot of other special protection characteristics about wind farms actually make them pretty stable. But that's for another course. This is basically to give you an idea of what wind is all about. Oops. Here's a little breakdown of a wind generator. The blades here, and they can pitch. Here here you have brakes. You have a motor and gearing, which can actually turn the turbine to whichever way you want it to go. You got weather station to help control the direction. This wind speed, with the blade reaction. And you have a gearbox. You can see the gears. Big gear driving a little gear, making the little gear spin faster. The generator back here with multiple magnets, so that we end up with high speed, high frequency, even though we have low blade spin. Okay, a couple interesting slides here. This one shows how in green we have, this is typical load in the Texas area. Typical load back in August 2011. Okay, the load here, but here's our wind. The wind generation, unfortunately, is usually at night, and it's usually when the load is down. So we have a mix match a little bit here with the load. The wind is down when the load is peaked. But solar is the opposite of that. Solar you have when during the day when you have the load, so the solar matches better with load. But wind, if we could store it, and there's a lot of that being planned, I mean stored electric vehicles, stored energy in the batteries of electric vehicles. A picture of everybody had an electric vehicle and we were using the inverters from solar power, whatever, to charge up cars. Well, what if we use wind at night to charge up cars, and during the day we can use that battery storage, and then we end up using our nighttime wind when we get it at night for daytime use. So there's things like that that are being planned. So that's an interesting graph. Here's another one about actual wind output as a percentage of total installed wind capacity. So we've installed quite a bit of wind, okay? Yet what we're actually generating is not close to our installed capacity. So just because you put wind turbines out there doesn't mean you're going to get the energy. So there's a matching factor, conditions change factors. It's a good source, but we still have a ways to go. We're trying to use wind. It's at night and it's not as reliable. When you put up a nuclear plant, you've got that power there 24/7, 7 days a week, all that kind of stuff. But on wind, it's variable. All right, solar. This particular type of solar is reflective solar. These mirrors, which are motor operated, are pointing the sun rays up to a boiler. So the boiler gets heated up, and that ends up running a steam turbine again. And that steam turbine then has condensers where we make the water go back to, the steam back to water, pump it back up in there, superheat it again. So a reflective solar system like this ends up with a steam turbine, etc. Then you have the photovoltaic type solar systems where the sun is converted into electricity. Now the sun energy into electrical energy, the electrical energy, each one of these little dinky cells, there's one little cell, but that's made up of multiple cells in itself. A little cell only produces 1.2 volts and maybe 20 milliamps. It's not huge. But if you take the 1.2 volts and put 100 of them, now you have 120 volts. If you put them in series, still at 20 milliamps. So then you put 100 rows, 100 of those columns wide, and now you take 20 milliamps and you make it 20 amps. So then if you have 100 by 100, you end up with 120 volts, 20 amps. Now you're starting to get somewhere. So the more cells that you put out there, the more voltage, the more current, and they're actually installed in series and in parallel to increase voltage, increase current, and when the sun's there, you're producing DC power. DC power is then usually used to charge batteries. The output, the floating part, goes to an inverter, raises up to 60 cycle, sync that on with the power system, and you end up with grid tie type power system. So that's a solar voltaic, which is not reflection, it's actually conversion. Still got a ways to go on that. The efficiency of these panels are still in the order of 20 to 30%. That's what makes so much solar panel for the energy. But once we improve the efficiency of that, you'll see much more solar at a cheaper installed cost. Here's another way of looking at the solar voltaic systems. The solar panels go into a power conditioning and control unit where the batteries getting charged and the output AC is then connected to loads. You can either have in some, like in residential, you can have some of the loads powered strictly by the solar and some powered by utility. It's pretty hard to power your refrigerator from solar. So you have a grid tie where surging and those types of things come from the utility, and yet you offset with solar. And that's kind of how things are going. Then we have what's called distributed generation, which is small generators all over the distribution system. This is anywhere from solar panels, wind systems, small wind turbines, to small micro generators providing voltage in small voltage plants throughout the distribution. some advantages. Steps up the voltage in the system where you need it. There's a little bit of it offsets and delays the construction of large plants. It has an improved reliability factor. Instead of one big plant going down, you might lose one small generator here or there. You actually have reliability. So you're starting to see the micro generators. Now we're getting into microgrids, where you might take a university campus, have some types of generation, some automatic switchgear, and have its own islanding capability from the utility. If the utility crashes, you still got your system running on a microgrid concept. Okay, so there's a lot going on in that area. Okay, now to summarize the module on power plants, we talked about the different types of power plants, the steam and nuclear, wind and solar. Okay, we explained the different type of equipment used for heating and cooling and recycling water and converting some of the energy into electrical energy, the solar and what have you. Then we've identified, well, when you start to use the simulator, you will see, circles for generators and squares for substations. We're going to start to get familiar as you start operating the simulator. But we want you to understand what it is you're operating on a simulator with this theory. Okay, so you're going to be able to learn how to use the simulator actually after you start using it, which is going to be coming up.